Cool, that seems to work. Great, so hi everyone from my side, I'm Johannes. Super happy to be here today, first time at this Deep Learning Summit. And yeah, my topic for today is going to be a lot about how you can treat training data much more like an actual software artifact, right? So something like, a bit like source code. And I just heard from the presentations you heard so far that this is becoming much more of a topic, how you can not have like your CSV file somewhere stored on a server, but more have something like an actual source code or artifact. Very briefly, before I give this talk, what is the goal of this talk? I mainly want to do two things, which is first give you some food for thoughts about how you can think about training data, like what kind of things changed in tech stacks so that we can treat training data differently and really just treat scratching surfaces on some really, really cool technologies. And in advance, I also have my contact slide on the last slide, but if you have any questions, please don't hesitate to contact me. I'm also here at the exhibition stand. Very shortly about myself, so that you know who I am. I'm Johannes. I'm a data scientist and engineer by heart. I co-founded Kern and previously before that built an AI consultancy. I'm mostly working on natural language processing, but I also get excited about anything in software engineering, and I'm a big fan of football and books and art. Cool, that's about me. And I give you a very short intro about what data-centric AI is about, what the ideas are. And to have everyone on the same page, just very simple, I want to give you one sample use case, which is just like a classification NLP. We have something like topic modeling, different texts, and we now want to predict, like, is this about sports, is this about politics, is this about anything else, right? Those are like classifications, and I'm going to jump a bit between use cases, sorry for that, but just to have everyone on the same page, this is like the kind of things we're talking about, how we can prepare the training data for that. And what we've seen very many times in the past is basically that as the engineer, as the scientist, you oftentimes are in a misery. You have like your chain, your workflow, your steps of things you need to do to build like the actual application. And there's like this one major part, which is basically building the training data. And you oftentimes don't have that much of influence of building the training data, right? You have bottlenecks, like working with the business units. When you get the data, it's oftentimes like a spreadsheet, and you don't have too much understanding of how well it's constructed, how good the quality is, and basically it just slows down the iterations. So that's not what a software artifact would look like, right? So we think about how can this change. And data-centric AI is exactly about this. If you think about a supervised learning use case, which consists of like your algorithm, and of course like your labeled data. On a model-centric approach, you think a lot about, okay, how can I, if I fix my data, how can I improve the quality of my outcome just by building more complicated problems, more complicated solutions. And then the data-centric perspective is more about how can I change the inputs and the outputs of the data that I have so that I can systematically engineer this. And to make this more concrete, I'm going to divide this topic into three small parts, which is basically about how you can prototype something in a data-centric approach, right? If you have zero labeled data and you want to scratch, like build something from scratch. The second thing is about how you can, on top of an existing labeled data, improve the outcome of your model continuously. And the third thing is a bit more researchy topic, which is about how you can make really complex problems much easier. Cool. I'm starting with the first one. And the first technology I want to show you is basically weak supervision. And it got a lot of attention in the last years. And if you think about it, putting all the magic beside, it's really a lot about how you can integrate information for machine learning, right? So the idea is you have an unlabeled data set and you now want to label something from scratch, like you have this cool idea that you want to work on as a side project, or you have like the small POC in your company and you don't want to label everything from scratch. You think about heuristics. And a heuristic, I'm going to go into more detail in a second, really doesn't have to be perfect, and it's just giving you an idea about what kind of label could fit to one of the records. So we have like basically a matrix where the rows are the records, and for each record you have multiple heuristics, and they basically just say something like, this is related to news, this is related to politics, and so on. And they can be conflicting, they can be overlapping, it doesn't matter. This is really just a very simple framework in which you build multiple heuristics and they all give a vote. And the ultimate goal in weak supervision is to synthesize them, right? So that you create a denoised label set from your heuristics, right? And if you think about this visually, you have like your vector space, your different vectors, and you basically try to build clusters with those heuristics. And you can already see they might be overlapping, they might be conflicting, but you don't care too much about this. And those kind of heuristics could be super simple labeling functions, right? Really just taking as input a dictionary and then predicting a string that should be the label on top of this. But it could also be like an active learning model that you just pull and train on a few of the manually labeled records. It could be zero-shot classifiers, which work perfectly for this, because zero-shot typically works out of the box, but not for every case. Or it could be like end-to-end labeling, and you really don't know how great of the quality is that they produce in labeling, but it could be a heuristic. And weak supervision is all about you not worrying about how to integrate them. Just think about one heuristic that could be a good idea and just push it into the weak supervision framework, basically. And from there, the job is done. I wanted to show you one example in NER, because it's a bit more complicated. And for instance, we here want to detect people, organization, and locations. And one example could be just a super simple labeling function where we look into different chunks and try to see what kind of conferences we know about that we can find. The second one could be using Spacy to, for instance, find chunks in the data that are related to people. And the third one could basically be just a model from Hugging Face, right? So just out of the box. And then the idea of weak supervision is that you can just integrate them very easily. The algorithm basically does the job for you there, and you just define those different kind of heuristics and they do the labeling for you. That's pretty much straightforward weak supervision, but it has a lot of really, really cool advantages. And I'm going to explain to you more what's so great about weak supervision. So let's think again about that we have our unlabeled data set. We now to build our first automations on top of this and then label efficiently, right? So we came up with our first set of heuristics, and we now basically carve out the obvious examples. So for instance, the data sets that we can, with high confidence, label automatically. Then we basically reduce them from the unlabeled set. And now we also have the exact examples that are hard, that are difficult to identify, that are difficult to label because they have like conflicting overlaps and everything. So we label them manually. And now what gets super interesting is we can use approaches like neural search when you have, for instance, your raw records also embedded using like a large language model or anything. You can also use neural search to not only randomly select the labels you want to label next, but really use this like, for instance, an outlier-based approach, right? So for instance, you have this space, and now think about what are the next labels that would cause me headaches in the training, which would be, for instance, this one, right? Because it's so different from the other records, I just want to label this one next. And from there, go iteratively, right? So the key idea here is basically, if you have an idea that you quickly want to prototype and you have like zero labeled data for this, weak supervision, which is a very, very basic framework, but it just works really well, is that you can think of different heuristics that work atomically speaking, and you don't worry too much about how they conflict, how they overlap and everything. You just use that information to label what you can label automatically, and you get further information about what kind of records are more difficult, that you want to pay special attention to when you do manual labeling. So this is something really great, and we've seen already that this is used in so many cases, like, for instance, radiology experts, sentiment analysis, chatbots, to really build data sets with hundreds of thousands of records in one afternoon. The data is not perfect yet, but it's really something that you can use for prototyping. So that's cool. That's for the first part, right? Having an idea, just wanting to prototype it quickly. But now we've also seen in the previous talks that you really want to care about not only the quantity, but really also about the quality, right? Because if you improve the training data, you get much better results of your model, which is obvious. And there I want to show next cool technologies. And one of the most interesting ones I like to see is looking into those typical standard data sets, those Hello World data sets like MNIST or Cypher, and really just looking into how good the quality is there, right? And it's mind-blowing because, for instance, in an ImageNet, you have a couple of hundreds of thousands of mislabeled images, right? It's crazy. I mean, you can look into the article at CleanLab, which is another really cool open source framework, which really just shows that also in your Hello World examples, you have so many wrongly labeled data sets, right? And the idea is, how can I fix this? And here comes confident learning into play, which is basically the assumption that you have some kind of better than random guessing model. And this could be like your weekly supervised labels, this could be a production model, it really doesn't matter. Just something that gives you labels better than random guessing. And now what you can do is you can compare your noisy labels, which is the existing data set you have, and you can use your prediction, right? And typically, models not only give like discrete predictions, but so many models can also give you continuous predictions, like the confidence scores. And so the idea is, how can I use this? And confident learning is simple in its idea, but it's brilliant in execution. And if you basically compute the metrics of the confusion metric, sorry, not the confusion metrics, the label metrics, what you can do is you can compare how many times is the prediction the same as my noisy label, and from there you can estimate the number of errors, right? Because if you now compute like the diagonal and take the sum of this, you can estimate how many of those records should be labeled correctly, and even more interesting, how many of them have errors. Again, this is not perfect, and this relies heavily on how good your production model is, but it gives you an incredibly good estimation, right? And basically for free. So what we can see for here, for instance, based on the production model, this would estimate that 25% of our records are labeled incorrectly, which is really not good. You want to look into this. And what's the next step? You have your model outcomes, so the prediction confidence scores, and you can use them, because looking at the first row, 70% confidence, 10% confidence, and 20% confidence, that's not uniformly distributed. It has a skew towards the first prediction. So we can say that the first prediction is rather secure, whereas the second one basically is almost uniformly distributed in confidence. So the second one really is one we want to look into. And because we know that 25% of our data set is likely to have errors, we can just order our records by the model confidence of the predictions, and then look into exactly those records that have high chance of being labeled incorrectly. Right? Those are the records that you, as a data scientist, you will have headaches during the model training when you use those data sets. So those are the ones you want to look into again with your colleagues, with crowd workers, doesn't matter, but those are records that influence a lot the model training. You also have some very straightforward examples, and this again is one that is not too high-tech, but it's still interesting. It's basically if you have multiple people working in a data set, you can do things like internet data agreements, right? This is something we see in the past. It's basically no-brainer that if you have the chance to label with a couple of people, you can estimate how often they align, and by this also can estimate what's the human performance benchmark. Because think about how often was your model measured towards, is this 100% accurate or not? I mean, with a human performance benchmark, you can set the actual expectation of what the model will most likely achieve or what's expectable, which is, as we all know, almost non-case 100% accuracy or precision. And what also super interesting, if you implement those heuristics, those are basically super interesting metadata to your records, right? Because, for instance, if I implemented a heuristic that says, if my record starts with a digit, then it's typically clickbait, and I have a 95% precision on this heuristic, whereas my colleague, Simon, has a 75% precision. This is basically telling us that Simon and I need to discuss about this heuristic, right? Because we have a different understanding of this heuristic, and therefore a label bias. So weak supervision, what I'm trying to say, is not only interesting to give you something from the start, to label something from scratch, but it's also super valuable for data management. Right? And if you look into this example, it starts with digit. One idea would be, for instance, if I want to debug it, to look into it and see if I only have it as it is, it has a precision of 83%, and now I want to analyze it further, look into the records that exactly have this heuristic, and then now maybe see that it's more the happy texts that start with a digit that are clickbait, and so I can optimize this. Again, this is mostly for data management, right? So you really see where are the records that have like a lower confidence, how can I optimize this? Okay, lots of input. The main idea is, how can I, as the engineer, gain more control and transparency into my data, right? Where can I find exactly those slices that cause me headaches that I want to look into with colleagues again maybe, so that I can continuously improve my training data set, right? Because it's basically so much of the formula of my prediction outcome. Okay, and now the third part gets a bit more researchy, and I hope you get excited about this, because I get super excited about this. It's basically how can you make a complex problem easier. And if we look into the last 3 or maybe 4 years of natural language processing, and you look into what enabled breakthroughs, it's mainly been about building vector spaces, right? Building really, really good embeddings. So you have like your large language models, your transformer models on Hugging Face, and the idea is that if you have a very good concept understanding of your data, you can build vectors that represent your data very well, right? You put unstructured data into structured latent vector space. And the idea is that if you have a good model that is able to do those transformations very well, sentences that are similar, like in sentiments or in intent or whatever, they are close to one another. And ones that aren't are more different, more distant. And why this is working so well, and why we are also using like machine learning algorithms from the last 70 years or something like this, is because if you do this, if you have a well-performing transformer model to calculate vector spaces, you have a very simple problem at hand, right? Building on such a vector space, a well-defined room to differentiate between, for instance, intents like cancellations, prejudices, and feedback, it's not difficult anymore. And this is where NLP really has its breakthroughs in the last years. So this is basically labeling, right? You have your vector space, and you want to have a gray vector space turned into a colorful vector space. And you want to use your data management to find, for instance, red points that should actually be blue, things like this. But the vector space doesn't change. And this is where there's another opportunity, right? So in so many cases in practice, you don't have your perfect vector space transformers, right? You have very good baselines, very good transformer models, but if you have like a transformer model learned on or trained on Wikipedia data, and you now put this into a domain where you work on customer mails like in some service desk, basically your embedding becomes much worse. So how can you improve on this? And this is also what similarity learning is all about, right? It's basically about going from a complex problem to a more simple problem, so you can again use machine learning algorithms of the last 70 years. And I want to give you one example, which is basically using the super popular sentence transformer library, which I guess many of you have already heard of. It's basically just the high-level API of transformer models from Hugging Face. So what you can do is you can import the library, and from there just say I want to use my transformer model like Distilbert, for instance. And now I don't want to train or fine-tune the output of the model, so I don't want to train the actual task, but I want to train the understanding of the model. So what I don't do is I have my labels, this is a happy sentence with the label positive, but instead I have pairs of sentences, right? For instance, my first sentence and my second sentence, and I now have a continuous label which explains the similarity. And if you think about it, this again makes perfect sense, because what you're telling the model is compute whatever kind of cosine similarity you have for those sentences, but how different are they in your current vector space? And the label I give you is the distance that they actually should have. And you can then again, of course, do this for multiple pairs, not for one only, but for, again, thousands. And this basically simplifies any downstream task, right? Because if you, again, build a better vector space, it doesn't matter if the downstream task is classification, span labeling, summarization. It really doesn't matter. That's the cornerstone of NLP. And we see this. We see that this is helping so much. But the foundational problem you have with similarity learning is basically labeling similarity is incredibly difficult with consistency. You can just try labeling in a very short session, try label 10 pairs, and your idea of similarity changes when you label the first record and then you label the 10th. It's incredibly difficult. And then it's a quadratic problem, right? So if you have 1,000 texts, you already have 999,000 pairs. So you really want to look into what kind of pairs do you want to label. And this is what I meant with research. We basically build a lot. We have already a cool product, but we are doing a lot of research, and this is basically our most active space of research. We're basically building tons of use cases in that segment, but again, it's still active research. Okay, looking at the time, I want to do a very short summary. So basically, the first thing I talked about is weak supervision, right? And I want you to think of weak supervision not as the magic ingredient that is all of a sudden going to give you perfect labels, but think of it as an interface, right? You don't have to worry about each and every heuristic. You just think of one, if it makes sense, integrate it, and see the results. So that's really cool. And you can use it to automate large parts of what you really don't need to label manually. And you can combine this to improve your manual labeling, right? You can, for instance, look into exactly those kind of records that cause you headaches, that you want to pay special attention to, that you want to send to your colleagues or crowd workers. So use that. And you can use it, for instance, with confident learning to really show, like in combination, for instance, with a production model, how large is my error rate? Or what is the estimate of my error rate? How can I improve on this? And like all of those techniques basically have so many intersections that just make them better. And then something for the future, I mean, you can easily build your own prototypes and then encourage you to give similarity learning a try. It's basically just simplifying your problems at hand, because this is what transformer models excel in. But still, they are like trained on the specific domains. And if you don't have the transformer fitting your very domain, you can change that with similarity learning. I have some cool resources to dive into, so if you find this interesting, I can only recommend a couple of cool papers. One of them is basically about weak supervision, the data programming paper, which is from the founders of Snorkel, which is basically the company that put life into weak supervision again. Confident learning, which is, again, a very basic idea, but it's really, really interesting and straightforward to implement. There's a great article about this. And for neural search, like if you want to look into how you can navigate through your data and manual labeling very easily, I can recommend open source databases like, for instance, Quadrant. And there are more articles, so if you want to dive really deep into this or you have one specific question, please reach out to me. We also did our own research, so I'm also happy to share this. And I get very nerdy and geeky about this. It's basically a paper that we published this year in Valencia at the NLDB, where we also share a lot about how you can actually apply those techniques. And last thing, and this is, excuse me, a very short advertisement, we are open source, so you can basically just look into this on GitHub, load it yourself and give it a try. It's completely open source, and we also have a booth at the exhibition stand. So if you want to look into this, let me know. Thank you so much. If you have any questions, super happy to answer them now or at the coffee. And yeah, thanks for having me.